AudioBooksTube is glad to produce, publish, and offer. What is reality? By Sage D. Esotreasure. Imagine a simple apple resting on a table, glistening under the light. A sharp knife is poised in your hand, ready for action. With a swift, precise motion, you slice the apple in half. What was once a whole fruit is now two equal halves, each revealing the soft, white flesh inside. But your curiosity compels you to go further. The halves become quarters, and the quarters transform into eighths. Soon, what started as a vibrant apple diminishes into an array of smaller pieces, each a delicate section of the original fruit. As your knife glides through the apple's flesh for the 14th time, you notice something astonishing. Those soft pieces of fruit are composed of countless plant cells, each one a building block of life. With every additional cut, you disassemble these cells, reducing them to complex molecules of carbon, hydrogen, and oxygen. Eventually, after a few more deliberate slices, the apple breaks down into an astonishing 10 to the power of 27 individual atoms. You find yourself pondering, is this where the division ends? Surely, a sharp knife has more to offer. Emboldened by your progress, you continue the dissection, diving deeper into the atomic realm. Each slice peels away the outer layers, revealing a swirling cloud of electrons surrounding an almost non-existent nucleus at the center. This nucleus, a minuscule fraction of the apple's original size, houses protons and neutrons, which in turn consist of even smaller particles known as quarks and gluons. Now, you stand on the precipice of the subatomic world, where the rules shift from the concrete to the uncertain. The apple is no longer a fruit, it has transformed into an ethereal wave, existing within a field of quantum possibilities. Have you finally arrived at the fundamental components of the universe? Not quite. With more determination, you press on. After countless slices, you encounter a reality where quarks and electrons appear as vibrating strings, mere trillionths of a trillionth of a meter across. In this realm, the fabric of existence becomes perplexing, filled with extra dimensions that challenge the very concept of space and time. Here, fundamental blocks of reality seem impenetrable, yet the mystery deepens. Perhaps this universe is nothing more than a simulated construct, whirring away on some superdimensional computer. Or maybe our tangible reality is simply an illusion, a holographic projection masking deeper mathematical truths. What, then, is reality? This question has occupied human thought for millennia. Can we truly grasp the essence of existence? Can we dissect the cosmos, or are we simply scratching the surface? The apple, so real in your hand, raises further questions. You can hold it, smell its sweet scent, and taste its crisp flesh. But what does it mean for something to be real? The philosophical exploration of reality has deep roots. Isaac Newton, a titan of scientific thought, had his own way of engaging with knowledge. He would fold the corners of pages in his books to mark significant phrases or ideas. In an era devoid of mobile phones or social media distractions, concentration was easier for him. Yet in our fast-paced world, where distractions abound, finding effective tools for learning is vital. Enter Imprint, a modern educational app that seeks to provide a solution. If you desire to cultivate a lifelong love of learning, Imprint is tailored for you. Its innovative approach offers bite-sized lessons that engage the mind without overwhelming it. With beautifully illustrated and animated content, the learning experience is both interactive and effective. Topics range widely, from psychology and philosophy to physics and productivity. As you explore this rich library, you might find yourself engrossed in the mind-bending physics of time, or uncovering the intricacies of cognitive biases through works like Daniel Kahneman's Thinking, Fast and Slow. There's never been a better time to immerse yourself in the wealth of knowledge available. You can experience Imprint free for a full week by scanning a QR code or visiting their website. Plus, as a nod to those intrigued by the universe, you can enjoy a 20% discount on their premium subscription. Now, let's shift our focus to our ancestors, who roamed the earth long before modern comforts. For them, reality was straightforward. From the vast plains of Africa to the icy landscapes of northern Europe, they perceived the world through their senses. The snap of a twig in the woods could signal food or a lurking predator. Reality was immediate and often a matter of survival. In their daily lives, they lacked the luxury of deep contemplation about the nature of existence. But as human consciousness evolved, so did our understanding of reality. Evidence suggests that as early as 100,000 years ago, humans began to bury their dead, hinting at thoughts of an afterlife. These burial rituals suggest a burgeoning awareness of something beyond the physical realm, or recognition that there was more to existence than what could be seen or heard. With this evolution in thought came the emergence of spirituality, gods, and the quest for meaning. The divine could explain the existence of the apple and the sustenance it provided. For early humans, the answers to their questions about reality were often found in the realm of the gods, transcending the limitations of human understanding. However, not all minds accepted such simple explanations. Plato, a philosophical giant of ancient Greece, challenged the material world. Living in Athens in the 4th century BC, he sought to understand the essence of existence beyond mere appearances. His philosophical inquiries are encapsulated in the famous allegory of the cave. In this allegory, prisoners are chained in a dark cave, facing a wall and deprived of any knowledge of the outside world. The only reality they know consists of shadows flickering on the wall, cast by objects illuminated by a fire behind them. These shadows, a mere reflection of the true world, shape their understanding of reality. What if, Plato posits, this cave represents our existence? What if we are all prisoners, unable to grasp the real world outside? The shadows play tricks on the prisoners' minds, distorting their understanding of reality. They perceive a reality constructed from illusions, manipulated by unseen forces. In this light, Plato invites us to contemplate our own perceptions. Are we merely observing the shadows of a greater truth, limited by our own understanding? His allegory challenges us to break free from our chains and seek the deeper meanings hidden behind the facade of reality. The exploration of reality is a multifaceted journey, intertwining philosophy, science, and human experience. As we peel back the layers of existence, we may find ourselves grappling with the questions that have driven humanity for centuries. What is real? How do we discern truth from illusion? In our quest for understanding, we navigate through the complexities of our perceptions, aided by the insights of ancient thinkers and modern scientists alike. The apple, once a simple fruit, becomes a symbol of the intricacies of reality, a reminder that our understanding is always evolving, always expanding. So, as we contemplate the apple and the journey it represents, we realize that the pursuit of knowledge is an endless path. Whether through the lens of philosophy or the precision of science, the quest to understand reality continues to challenge and inspire us. We stand at the intersection of the known and the unknown, ready to explore further, to slice deeper, and to seek the essence of existence. In this grand narrative, the apple is more than just a fruit, it is a gateway to deeper inquiry, urging us to question, to learn, and to embrace the mysteries that surround us. And in doing so, we honor the legacy of those who came before us, those who dared to ponder, to explore, and to dream. Picture an apple on a kitchen counter, gleaming in the light. You take a knife, sharp and glinting, and prepare to cut into this vibrant fruit. With a decisive stroke, you slice the apple in half, revealing its crisp, white flesh nestled within a bright, green skin. What was once a single piece of fruit is now two distinct halves, each begging for further exploration. Encouraged by your initial success, you continue to slice. The halves transform into quarters, and those quarters become eighths. With every cut, the apple shrinks in size, morphing into smaller and smaller pieces, as if each slice unveils a hidden world within. By the time you make your 14th incision, you notice that the once solid apple now consists of countless tiny cells, each a living entity, part of a larger whole. You delve deeper into the apple's structure, slicing again and again. After a series of additional cuts, those cells break down into intricate molecules made of carbon, hydrogen, and oxygen. At this point, you've sliced through the apple enough times that it has been reduced to approximately 10 to the power of 27 individual atoms. You pause for a moment, pondering whether your knife can cut any further. Yet your knife, still razor-sharp, invites you to continue. You make yet another cut, pushing past the material realm into the atomic. The layers peel away, revealing a swirling cloud of electrons surrounding a tiny atomic nucleus. This nucleus is astoundingly minuscule, a mere fraction of the size of the original apple, but still solid in its essence. But you're undeterred. You press on, delving further into the atomic world. The nucleus splits apart into protons and neutrons, which in turn unravel into quarks and gluons. You are now entrenched in the elusive realm of the subatomic, a landscape where reality blurs into waves of potential rather than concrete matter. The apple is transformed into an ethereal construct, existing as a probability wave among countless fields of energy. At this juncture, it feels as though you have reached the boundary, the foundational elements of existence. But curiosity pushes you further. You make countless additional cuts, uncovering quarks and electrons that begin to reveal themselves as vibrating strings, each merely a trillionth of a meter in size. Here, the universe reveals itself to be a rich tapestry of dimensions, intricate and unfathomable. Perhaps what we perceive as reality is merely a hologram or a simulation, an intricate illusion projected by some higher dimensional entity. Alternatively, maybe all that we perceive is the result of a complex mathematical structure underlying the cosmos. So, what does it mean to understand reality? This question has been a fundamental pursuit for humans throughout history. The apple, so tangible and real in your hands, serves as a powerful reminder of this inquiry. You can hold it, smell its fragrance, and taste its sweetness, yet the question remains, what does it truly mean for something to be real? Philosophers have long grappled with the nature of reality. Consider Isaac Newton, whose method of learning involved folding the corners of pages in his books, marking phrases or ideas of significance. He lived in a time devoid of modern distractions, allowing for deep focus on the mysteries of the universe. In stark contrast, today's world bombards us with information and distraction, making the quest for knowledge both more challenging and more essential. This is where Imprint, an innovative learning app, comes into play. If you yearn for a lifelong journey of discovery, this platform is designed for you. Offering concise, engaging lessons, Imprint enhances your understanding without overwhelming your senses. With beautifully illustrated and animated content, the learning experience is both immersive and enlightening. The app boasts a diverse library covering subjects like psychology, philosophy, physics, and productivity. As you explore these topics, you might find yourself captivated by the mind-bending principles of time, or you could uncover the nuances of cognitive biases through works such as Daniel Kahneman's Thinking, Fast and Slow. Now is an ideal time to dive into Imprint's wealth of resources, with a free 7-day trial available by scanning a QR code or visiting their website. Plus, fans of knowledge can benefit from a 20% discount on a premium subscription. Reflecting on the human experience, consider our ancestors who lived thousands of years ago. For them, reality was straightforward. Whether traversing the savannas of Africa or braving the icy tundras of northern Europe, they understood their world through sensory experiences. A rustle in the grass might signal a meal, while the crack of a branch could indicate a predator nearby. Reality was immediate, often tied directly to survival. In their daily existence, they didn't have the luxury to ponder the nature of reality deeply. Yet as human thought evolved, so too did our understanding of existence. Evidence suggests that as early as 100,000 years ago, humans began to engage in burial practices, hinting at reflections on mortality and an afterlife. These rituals reveal a burgeoning awareness that reality extended beyond mere physical existence. With this growth in consciousness came the emergence of spirituality and the quest for meaning. The divine offered explanations for the mysteries of life, including the bounty of apples and other fruits. For early humans, the nature of reality often aligned with divine intentions, truths beyond human comprehension. Yet not all thinkers accepted such explanations. Plato, one of history's greatest philosophers, challenged the material world around him. Living in Athens in the 4th century BC, he sought to understand existence beyond physical appearances. His allegorical tale of the cave illustrates this philosophical inquiry perfectly. In the cave, prisoners are chained, facing a wall, entirely oblivious to the outside world. The only reality they know consists of shadows dancing on the cave wall, created by objects illuminated by a fire behind them. These shadows, mere reflections of the true world, dictate their understanding of existence. Plato invites us to contemplate our own experiences. What if we are all prisoners within our own minds, limited in our understanding? The shadows on the wall could be mere illusions, manipulated by unseen hands. As we navigate through life, we are tasked with breaking free from these shackles, seeking deeper truths hidden beyond the illusions we perceive. Plato's allegory pushes us to reconsider what we accept as reality, urging us to question the nature of our existence. The exploration of reality is a multifaceted journey, intertwining philosophy, science, and the breadth of human experience. As we peel back the layers of existence, we grapple with questions that have driven humanity for centuries. What is real? How do we distinguish between truth and illusion? Our quest for understanding navigates the intricate landscape of our perceptions, aided by the insights of ancient philosophers and modern thinkers alike. The apple, once a simple fruit, becomes a profound symbol of these complexities, a reminder that our understanding of reality is a continually evolving process. Thus, as we ponder the apple and the journey it represents, we recognize that the pursuit of knowledge is an infinite path. Whether approached through philosophical contemplation or scientific inquiry, the quest to grasp reality remains a compelling adventure. In this grand narrative, the apple symbolizes more than just sustenance. It serves as a portal to deeper inquiry, compelling us to question, to learn, and to explore the mysteries surrounding us. In doing so, we honor the legacy of those who came before, those who dared to dream, to seek, and to understand. Time, a relentless force, was ticking at a rate far beyond our usual perception. This extraordinary phenomenon, known as cosmic dilation, was anticipated, a testament to the mathematical principles governing our universe. This groundbreaking theory emerged over a century ago, revolutionizing our comprehension of space and time. The phrase "I think, therefore I am" echoes through the annals of philosophy, attributed to René Descartes. His profound reflections on existence have reverberated across generations. Yet Descartes contemplated more than just the essence of being. One cold night in 1619, while serving as a mercenary for the Dutch Protestant cause, he secluded himself in a small room to escape the winter chill. Although he had a background in engineering and mathematics, this particular night would lead to a remarkable epiphany. Confined to his sickbed, Descartes gazed around the room, his attention caught by a fly crawling along the ceiling. Suddenly, the insect took flight, darting from one wall to another, inspiring a question in Descartes' mind. How could he describe the fly's movement? He realized the need for a reference point to anchor its motion. While the choice of reference could be arbitrary, consistency was crucial. Moreover, he recognized that describing the distance from this point to the fly was insufficient. Direction was equally essential. Then, an enlightening thought struck Descartes. He envisioned using the corner where two walls met the ceiling as his reference point. By projecting lines along these walls, he could create axes that intersected at right angles. This ingenious concept allowed him to assign numerical values to the fly's position along each axis. Thus, he understood that three numbers could uniquely define a location in three-dimensional space, coordinates that would change continuously with time. Descartes' coordinate system may seem elementary to us now, but it laid the groundwork for understanding motion. Schoolchildren learn to use this system to comprehend position and movement. For professional scientists, establishing a Cartesian coordinate framework is often the first step in problem solving. Even after his death in 1650, Descartes' contributions continued to shape the scientific landscape. At the same time, a young boy named Isaac Newton was growing up in the English countryside. Newton would later harness Descartes' ideas, establishing a mathematical foundation for motion that became known as classical mechanics. In Newton's universe, time is an absolute entity, a universal clock ticking in synchrony across the cosmos, a notion everyone agrees upon. However, the concept of space is more nuanced. Galileo, a contemporary of Descartes and Newton, recognized that observers could define their own coordinate systems. Galileo was more inclined to explore the world through storytelling rather than strict mathematics. He used the example of being aboard a ship to illustrate his ideas. When a ship lay still in a harbor or glided smoothly across calm waters, passengers below deck would feel no difference. However, if the winds picked up, causing the ship to accelerate or navigate through rough seas, those inside would sense the change, plates and cutlery sliding off tables, and people swaying unsteadily. Galileo concluded that absolute rest could not exist in the universe. Instead, he asserted that all motion is relative and that the laws of motion should hold true for observers in unaccelerated states. Thus, the initial theory of relativity began to take shape. These concepts were woven into Newton's classical mechanics, enabling any observer in uniform motion to apply his three laws of motion to predict outcomes. A simple experiment illustrates this. Drop a ball on a train station platform and watch it fall to the ground. Now, repeat the experiment on a train moving at constant speed. The ball still drops straight down. However, if the ball is dropped while the train is accelerating, it may seem to veer backward or forward, defying Newton's laws. This perceived deviation arises because the coordinate system is accelerating. Once uniform motion is achieved, those fictitious forces disappear. This understanding of motion persisted for centuries until the enigmatic Scottish physicist James Clerk Maxwell unraveled the mysteries of light and, with it, the peculiarities of our universe. Maxwell's influence on science was profound. By the mid-1800s, he had mathematically unified electricity and magnetism, revealing their interconnectedness through a series of equations. This monumental achievement made Maxwell famous in scientific circles, yet he delved deeper, unearthing a startling realization: light itself must be an electromagnetic phenomenon, oscillating fields of electricity and magnetism. His equations also unveiled the speed of light, an astonishing 300,000 kilometers per second, but raised an intriguing question: relative to what? The need for an absolute rest frame emerged as a potential solution to save physics. Some theorists posited the existence of an ether, an invisible medium through which light traveled. Experiments involving light beams reflected off mirrors or electrical circuits aimed to demonstrate that motion relative to this ether was crucial to understanding light's behavior. However, this proposition posed a significant challenge to Galileo's relative motion principle. Why would electromagnetism adhere to an absolute state of rest while other physical laws remained indifferent? In 1905, a revolutionary physicist challenged this complicated paradigm. He proposed a unifying framework where the universe was not divided into two separate realms of physics, one governed by Galileo's principles and the other by electromagnetic phenomena. This physicist was Albert Einstein, whose theories of special relativity would fundamentally reshape our understanding of the universe. Einstein's insights revealed that the laws of physics are the same for all observers, regardless of their relative motion. He demonstrated that the speed of light is a constant, independent of the observer's frame of reference. In this new framework, the concept of time itself became fluid, altering perceptions of simultaneity and challenging the rigidity of absolute time. This paradigm shift marked the dawn of modern physics, paving the way for further exploration into the nature of reality. No longer could we rely solely on the rigid boundaries established by Newtonian mechanics. Instead, we were invited to explore a universe rich with complexity, one where time and space interweave in unexpected ways. Thus, the journey began, a quest to unravel the layers of existence, to comprehend the interplay of time, space, and motion. The world was no longer a straightforward entity but a dynamic tapestry of interactions and relationships, challenging our perceptions and inviting us to ponder the profound mysteries of the cosmos. In this unfolding narrative, the teachings of Descartes, Galileo, Newton, Maxwell, and Einstein converge, guiding our exploration of reality. As we stand on the shoulders of these giants, we find ourselves at the forefront of a new era, one that embraces uncertainty and complexity, forging a path toward deeper understanding. The legacy of these thinkers endures, inspiring us to continue questioning, discovering, and redefining our understanding of the universe. As we peel back the layers of existence, we recognize that reality is not merely a static construct, but an ever-evolving interplay of ideas and discoveries, challenging us to expand our horizons and explore the unknown. As the dawn of the 20th century approached, a revolutionary shift in physics was brewing. Albert Einstein's special theory of relativity emerged, reshaping our understanding of space, time, and motion. At its essence, this theory embodies the aspiration of a lazy physicist, the desire to explain as much as possible using the least amount of effort. Einstein proposed that all observers, regardless of their relative motion, should be able to apply Maxwell's equations to predict the outcomes of electromagnetic experiments. However, this idea came with a rather uncomfortable conclusion: all observers must measure the same speed for light. Such a notion posed a significant challenge to Newton's classical views on space and time. In Einstein's perspective, space and time are not the unyielding frameworks posited by Newton. Instead, they are malleable. Distances and durations can vary depending on the observer, creating a sense of relativity that may sound absurd in our daily experiences. Yet, experiments conducted at speeds nearing that of light have consistently confirmed this alteration in our understanding of time and space. A pivotal moment came in the 1960s, when scientists provided irrefutable evidence for the distortion of time through observations of a subatomic particle called the muon. This particle, a heavier cousin of the electron, possesses a fleeting existence of merely 2/millionths of a second before it decays into electrons and neutrinos. Muons are generated in the upper atmosphere, created when cosmic particles collide with gas molecules as they travel close to the speed of light. Physicists anticipated that these high-energy muons would travel about half a kilometer before disintegrating. However, what they found was astonishing. Muons arrived at the Earth's surface after traversing distances of many kilometers. The question arose: why did these muons appear to exist for so much longer than their predicted lifetime? The answer lay in Einstein's special theory of relativity and a particular quantity known as the Lorentz factor, which dictates the dilation of time. To comprehend this concept, it's essential to recognize a crucial outcome of special relativity. The speed of light is an absolute limit in the universe. No matter how much energy we exert, no object with mass can reach light speed. As velocities approach this cosmic limit, the Lorentz factor escalates, leading to fascinating consequences. For the muon, its existence might seem limited to a mere 2/millionths of a second. Yet, from the perspective of physicists observing it on Earth, its lifespan appears significantly extended, allowing it to reach the ground. This narrative also possesses an intriguing flip side. While scientists on Earth witness the muon's extended journey, if the muon were capable of observation, it would assert that it had only traversed a few hundred meters in its brief existence. Here, we see how both time and space can warp and dilate as speeds near that of light. Einstein further recognized that this speed limit has profound implications for the transmission of information. It asserts that nothing can travel faster than light. A classic illustration of this concept is that we do not see the sun as it is in the present, rather, we perceive it as it was 8 minutes ago. The light emanating from the Andromeda Galaxy began its journey long before humanity walked the Earth. When astronomers peer through their telescopes, they witness galaxies as they existed millions of years ago. Hidden from view is the universe in its current state. Instead, we are granted glimpses into the past, an experience defined by what is known as our past light cone. The further away an object is, the younger it appears. The implications of Einstein's insights were profound. With space and time varying for different observers, the concept of a universally agreed now vanished. The relativity of time meant that observers could disagree on how much time has elapsed. Einstein swiftly recognized that this dynamic undermined a cherished idea, synchronicity, the belief that two events occurring at distinct locations can happen simultaneously. In our everyday experiences, this notion seems fundamental to the rhythm of life. However, it is ultimately an illusion. To illustrate this, consider one of Einstein's thought experiments involving 3 people aboard a speeding train carriage. One person stands at the back, another at the front, and the third in the middle. As the train speeds forward at a uniform rate, they decide to conduct an experiment. The individual in the middle releases a pulse of light, which travels to the back and front of the carriage. Each end has a mirror reflecting the light back toward the center, and at the moment of reflection, both individuals at the ends raise their hands. In a practical setting, this experiment would be completed quickly, with human reaction time acting as a limiting factor. However, thought experiments allow us to sidestep these everyday constraints and focus on the underlying physics. From the perspective of those inside the train, everything appears symmetrical. Both light pulses travel the same distance and return to the center simultaneously, leading to the conclusion that both hands were raised at the same moment, an experience of synchronicity. Now, let's shift our focus to an external observer standing on the platform as the train speeds past. For the sake of imagination, let's assume this train is moving close to the speed of light. What does this observer perceive as the experiment unfolds? This is where things take a peculiar turn. The outside observer sees the light pulses emitted from the middle of the carriage and journeying toward the back and front. However, according to Einstein's special relativity, all observers must see light traveling at the same speed. This leads to an intriguing scenario. As the train speeds by, the back of the carriage moves closer to the light pulse while the front moves away, creating an asymmetry in the distances. Despite both light pulses eventually reaching the middle of the carriage at the same moment, the outside observer would note that the reflections and the hands being raised occurred at different times. This reveals the key point. synchronicity is dependent on the observer's frame of reference. Although Einstein was satisfied with the formulation of his special theory of relativity, he quickly recognized potential problems lurking beneath its surface. As he pondered these complexities, he laid the groundwork for future explorations into the nature of reality. In conclusion, the advent of Einstein's special theory of relativity transformed our understanding of space and time. It shattered the long-held notions of absolute frames of reference and synchronicity, introducing a universe where everything is interwoven with relative motion. The implications of this theory continue to influence modern physics, inviting us to embrace a world that is far more intricate and fascinating than we ever imagined. Gravity has always been a puzzle for physicists, but it was Isaac Newton who laid the groundwork for understanding it in the 17th century. His equations beautifully explained why an apple falls from a tree or how the moon orbits the Earth. However, Newton's framework relied on a fixed notion of time, where distances between masses could be measured in a clear and absolute way. Enter Einstein. With his groundbreaking theory of relativity, Einstein challenged the very fabric of how we understand space and time. In Einstein's universe, time was not a constant, rather, it was fluid, altering based on the observer's frame of reference. This fluidity raised the question, how could we meaningfully discuss the separation between masses when now isn't universally defined? The lack of a unique moment in time rendered Newton's conception of gravity inadequate. Einstein grappled with the implications, ultimately rejecting Newtonian gravity in its entirety and opting to reinvent the concept from scratch. The task before him was immense. Where could he fit gravity into his equations of relativity? Surprisingly, he discovered that gravity could be represented as a distortion in the very fabric of spacetime itself. This revolutionary idea took Einstein over a decade to refine, but by 1915, he had formulated the general theory of relativity, which we still use today to explain gravitational interactions. No longer was gravity merely a force acting between two masses, it became the curvature of spacetime itself. This profound understanding allows us to explore the universe and even navigate our everyday lives, like utilizing GPS technology. Einstein's conclusions about the nature of gravity extended far beyond simple calculations. They introduced a new understanding of the universe, one in which synchronization is impossible, where time and space can warp in extreme ways. The question of whether two events occur simultaneously now hinged entirely on the observer's perspective. This leads us to fascinating studies, such as the quasar research conducted in 2023. Did time really flow more slowly in the younger universe? From a personal perspective, 1 second back then felt just like 1 second. But as the universe has expanded, the light traversing it has been stretched. This unique nature of spacetime implies that what we observe in the distant cosmos seems to unfold more slowly than it actually did. A more extreme illustration of this principle can be found in the phenomenon of time dilation near black holes. In these gravitational wells, space-time bends to extreme degrees. As you approach a black hole's event horizon, your perception of time slows in comparison to observers far away. This slowing of time near a black hole and the stretching of light from the distant past share a fundamental similarity. Both are examples of how space-time can warp and bend, creating a universe where time is not a universal constant. From the early 20th century onwards, our understanding of time underwent a dramatic transformation. Einstein's perspective revealed that time is deeply personal. Your clock, whether mechanical or biological, ticks at a steady 1-second pace. However, others' clocks might run at different rates depending on their relative motion, their position in a gravitational field, or even their epoch in the cosmic timeline. The implications of this relativity are significant. Experiments have demonstrated this by sending atomic clocks on journeys around the Earth, leading to discrepancies in their measurements when they are reunited. The relative nature of time opens intriguing possibilities for future travel. Imagine spending time in the intense gravitational field of a black hole. While minutes pass for you, decades could elapse for those far away. Time, in essence, becomes a slippery concept, deeply influenced by the context in which it is observed. As you contemplate the apple resting just a couple of meters away, you realize that your perception of now is uniquely yours. This awareness can lead to some deep philosophical pondering. What is reality, and how do we define it? This existential inquiry begs the question, what is the universe made of? To explore this, we might consider the fundamental constituents of matter. In May 1932, a groundbreaking event took place at a laboratory in Cambridge, where British scientists Ernest Walton and John Cockcroft achieved what was once thought impossible: they split an atom. The headlines of the Melbourne Argus proclaimed this success, highlighting the monumental nature of their achievement. This breakthrough marked a pivotal moment in our understanding of reality, one that ancient philosophers had speculated about for centuries. Throughout history, thinkers have pondered the nature of matter. Was it infinitely divisible, or were there ultimate building blocks? Ancient Greek and Indian philosophers proposed that everything is composed of tiny indivisible pieces, now known as atoms. For millennia, this notion remained largely philosophical. However, the 18th century brought forth scientific evidence supporting the physical existence of atoms, not from the work of physicists, but from a botanist named Robert Brown. Born in Scotland in 1773, Brown traveled extensively to study plant life. In 1827, he turned his focus to tiny pollen grains floating on water. Under the microscope, he observed these grains behaving in a puzzling manner. Instead of settling calmly, the pollen moved erratically, suggesting that something smaller was in motion around them. This observation hinted at the existence of atoms and provided early evidence for their physical reality. This exploration of the universe's building blocks continues to this day, intertwining philosophy and science. The quest to understand matter leads us deeper into the complexities of reality. In conclusion, gravity, time, and the very fabric of our universe present a tapestry of ideas that challenge our perceptions. Einstein's insights into relativity and the nature of time revolutionized physics, while the pursuit of understanding matter has transcended centuries of inquiry. As we delve deeper into these mysteries, we continue to expand our knowledge of the cosmos and our place within it. Grains dancing and jiggling in the liquid, he wondered if this lively movement suggested that the grains were alive, perhaps propelling themselves through the water. Yet, even chalk dust, an utterly lifeless substance, exhibited the same jittery behavior. Brown's observations sparked curiosity, but the explanation for this peculiar motion would elude scientists for decades. It wasn't until 1905, famously dubbed Albert Einstein's Annus Mirabilis or Year of Wonders, that the scientific community would receive a breakthrough. While Einstein is often celebrated for his special theory of relativity, his revolutionary contributions extended to quantum physics as well. In that remarkable year, he provided a comprehensive explanation for Brown's puzzling observations through the phenomenon known as Brownian motion. Einstein's insight was both simple and brilliant. The jiggle of the pollen grains was not the result of their own propulsion, but rather a result of collisions with surrounding water molecules. At first glance, the notion seems absurd. How could a minuscule water molecule, weighing a fraction of the pollen grain, exert enough force to create such noticeable movement? To grasp this, consider yourself in a massive concert crowd, engulfed by throngs of fellow concert-goers. As the crowd surges to the left and right, you find yourself swaying along, unable to predict the direction of the next push. Despite your attempts to hold your ground, you inevitably jiggle due to the relentless forces surrounding you. Einstein articulated that the Brownian motion observed in pollen was akin to this chaotic crowd experience. Every second, countless water molecules collide with a pollen grain, resulting in the seemingly random fluctuations that make it dance in the liquid. By calculating the size and frequency of these collisions, Einstein confirmed the existence of an immense number of minuscule water molecules. Thus, the atomic hypothesis shifted from speculation to reality, establishing atoms as the fundamental building blocks of matter. However, just as the existence of atoms was being validated, a new complexity emerged: the recognition that atoms were not as simple or stable as previously believed. In 1896, Henri Becquerel and Marie Curie discovered radioactivity, revealing that certain elements could transmute into others, releasing subatomic particles in the process. Then, in 1897, J.J. Thomson's discovery of the electron introduced the notion that atoms contained even smaller constituents. This ignited a race among scientists to uncover the structure of the atom itself. Thomson's work earned him the Nobel Prize in 1906, but it was Ernest Rutherford, often regarded as the father of nuclear physics, who would profoundly change our understanding of atomic structure. In the early 20th century, Rutherford enlisted two young researchers, Hans Geiger and Ernest Marsden, to explore the atom's interior in a darkened lab at the University of Manchester. Their task was to detect tiny flashes of light produced by particles colliding with a fluorescent screen, marking their impact. Initially, their experiments yielded results consistent with expectations. But as Rutherford encouraged them to modify their approach, they were poised to witness a groundbreaking moment that would alter our understanding of physical reality. When they investigated for flashes in areas where none were expected, they encountered an astonishing phenomenon. Rutherford was astounded. He described the moment as one of the most incredible of his life. By this point, he had already been awarded a Nobel Prize, but what he and his team discovered would revolutionize the atomic landscape forever. The background of this breakthrough was J.J. Thomson's earlier findings, which hinted at the existence of electrons. Thomson proposed a model of the atom, the plum pudding model, where electrons, the plums, floated in a positively charged pudding. This model raised a crucial question: how was the electric charge distributed within the atom? Rutherford's experiments aimed to test Thomson's model. He directed a beam of alpha particles, which are essentially charged helium nuclei emitted from radioactive sources, toward a thin sheet of gold foil. The expected result was that these particles would experience minor deflections as they passed through the positively charged pudding of the atom. As Geiger and Marsden observed, many alpha particles zipped right through the foil unimpeded. However, they occasionally noted that some particles were deflected at sharp angles, a deviation that contradicted Thomson's model. The implications of these observations would soon become clear. One day, at Rutherford's suggestion, Geiger and Marsden focused on the surprising scattering patterns of alpha particles that strayed far from their expected paths. They were stunned to find alpha particles scattering at acute angles, some even bouncing back toward the source. Rutherford famously likened this to firing a cannonball at a piece of tissue paper and having it bounce back. From these perplexing results, Rutherford concluded that instead of being dispersed throughout, the positive charge in the atom must be concentrated in a tiny nucleus. This dense core, surrounded by orbiting electrons, was responsible for the electromagnetic repulsion that caused the unexpected deflections of the alpha particles. The structure of the atom, once thought to be a simple mix of positive and negative charges, was revealed to be far more complex and organized. Rutherford's revelations prompted the scientific community to reevaluate the fundamental nature of matter. His work paved the way for future research in nuclear physics and led to the development of the planetary model of the atom, where electrons orbit a dense nucleus much like planets around the Sun. This new understanding laid the groundwork for the further exploration of atomic structure and behavior, leading to the discovery of additional subatomic particles and the development of quantum mechanics. In the unfolding narrative of science, we see how curiosity and the quest for understanding have driven humanity to uncover the intricate details of the universe. The initial observations made by Robert Brown about pollen grains in water spiraled into profound discoveries that reshaped our conception of reality itself. The interplay of chance, insight, and collaboration among scientists like Einstein, Thomson, Rutherford, Geiger, and Marsden illustrates the power of human ingenuity and the continuous evolution of knowledge. As we delve deeper into the atomic world, the questions continue to grow, sparking new lines of inquiry and exploration. What lies beyond the atom? What mysteries remain to be unveiled in the cosmos? Each answer leads to more questions, driving the relentless pursuit of understanding that defines science itself. With each breakthrough, we inch closer to grasping the complexities of our universe, revealing that the quest for knowledge is as infinite as the cosmos we seek to understand. The study of atomic structure is a complex and evolving narrative that begins with Ernest Rutherford's groundbreaking insights. Rutherford's experiments revealed the composition of the atom, leading to a radically altered perception of reality. At the heart of the atom lies the nucleus, a dense core comprised of positively charged protons, while negatively charged electrons orbit around it. This seemingly simple model, however, opened a Pandora's box of questions that scientists have sought to answer for over a century. Rutherford's pivotal experiments demonstrated that alpha particles, which are substantial in size and mass compared to electrons, could be deflected at various angles when they collided with the nucleus. The unexpected scattering patterns led him to conclude that the nucleus was not only massive but also concentrated in a way that allowed it to exert strong electromagnetic forces on the electrons. Consequently, the majority of an atom's volume is occupied by empty space. This revelation shattered the illusion of solidity that we associate with matter. Every tangible object we encounter, be it a chair, a tree, or even ourselves, is constructed from atoms that, paradoxically, consist mainly of voids. This realization is unsettling. One might wish to hold on to the idea that, although atoms are largely empty, their constituents, the nucleus and orbiting electrons, are real entities. Yet, as physicists continued to explore the atomic landscape, it became clear that the nucleus itself was not as simple as it appeared. The story takes a somber turn in 1915, during the throes of World War I. A sniper's bullet claimed the life of Henry G. Moseley, a brilliant scientist who was on the cusp of significant discoveries in atomic theory. Moseley had originally enrolled as a soldier against his family's wishes, compelled by a sense of duty. Before his enlistment, he was making strides in understanding the atomic nucleus. Born in 1887 to an Oxford professor, Moseley had excelled academically and joined Rutherford's team in Manchester in 1910. His innovative use of X-rays to bombard different elements unveiled new patterns and energies that hinted at the deeper structure of atoms. Moseley's work indicated that the emissions of X-rays varied with the atomic weight of the elements. In this context, the Dutch physicist Antonius Johannes van den Broek proposed a groundbreaking idea. If electrons have a fixed negative charge and mass, perhaps the nucleus was composed of distinct positive charges that balanced the electrons. This insight suggested that the only difference among elements was the number of positive charges within the nucleus. As each atom must remain electrically neutral, the number of protons would equal the number of electrons, dictating the atom's chemical properties. With this understanding, Moseley rearranged the periodic table according to what we now refer to as atomic number, establishing a system that remains in use today. The implications of his work were profound. Niels Bohr, a luminary in quantum mechanics, later reflected on Moseley's contributions, acknowledging that the true transformation in atomic theory stemmed from his work rather than Rutherford's earlier findings. Moseley's untimely death left the scientific community pondering the potential advancements that could have emerged from his genius. As the war progressed, Rutherford continued to push the boundaries of atomic science. His investigations into radioactivity clarified the nature of elements. He described hydrogen as the simplest element, comprising a single proton and one electron, while helium had 2 protons and 2 electrons, and so forth. By systematically exploring the properties of various elements, Rutherford introduced the terms proton for the positively charged particles and identified the neutron, a neutral particle that resides within the nucleus, in 1932. This process of refinement transformed the chaotic picture of atomic structure into a more straightforward one, consisting of just 3 fundamental particles: protons, neutrons, and electrons. Every element in the universe could be categorized based on these components, leading to the realization that all matter, including the 92 naturally occurring elements and their isotopes, is constructed from these essential building blocks. In this newly understood atomic framework, electrons zip around the nucleus at nearly the speed of light, while the nucleus itself, composed of protons and neutrons, holds the atom's mass. However, Rutherford's model encountered a critical challenge. The prevailing understanding of electromagnetism, as articulated by James Clerk Maxwell, indicated that an accelerating charge must radiate energy as electromagnetic waves. Since orbiting electrons are perpetually in a state of acceleration, they should lose energy over time, ultimately spiraling into the nucleus. This posed a significant dilemma for the stability of the atom as conceived by Rutherford. As researchers delved deeper into the quantum realm, it became evident that a new theoretical framework was required to reconcile these contradictions. The limitations of classical physics were becoming increasingly apparent, prompting a shift towards quantum mechanics, which would later provide the necessary explanations for atomic behavior. The implications of these discoveries extend far beyond mere academic interest. They challenge our fundamental understanding of existence. The notion that atoms are predominantly empty space forces us to reconsider the nature of reality itself. Solid objects, such as an apple or a chair, are, at their core, made up of atoms that are largely void, leading to the profound conclusion that what we perceive as solid matter is, in fact, an intricate interplay of forces acting at the atomic level. Furthermore, the ongoing quest to understand the atom continues to inspire new avenues of research. Scientists are now probing the mysteries of dark matter, quarks, and other subatomic particles that challenge our current understanding of the universe. Each discovery adds another layer to the tapestry of knowledge that humanity is weaving, reminding us that the more we learn, the more questions arise. As we reflect on the journey from Rutherford's initial revelations to the ongoing exploration of atomic structure, we see a remarkable narrative of scientific progress, collaboration, and serendipity. The lives of individuals like Henry Moseley and the discoveries they made serve as a testament to the interconnectedness of knowledge and the importance of nurturing curiosity. As we continue to explore the mysteries of the universe, we are reminded that the quest for understanding is an unending journey, one that beckons us to probe deeper, ask bolder questions, and redefine the limits of what we know. In the ever-mysterious realm of particle physics, the discovery of the muon represented a turning point that raised more questions than it answered. This elusive particle, which decayed in a mere 2/millionths of a second, sparked curiosity and confusion. Why does the muon exist if it appears unnecessary for the fabric of reality? As particle physicist Isidore Rabi famously noted, the muon disrupted the previously tidy landscape of atomic structure. Its existence marked the beginning of a cascade of discoveries that unveiled a bewildering array of particles emerging from experiments throughout the 1960s, plunging scientists into a chaotic subatomic world. As researchers delved deeper into this chaos, a clearer picture began to emerge. The development of what we now call the Standard Model of particle physics introduced the idea that protons, neutrons, and many other particles are not fundamental building blocks. Instead, they are composed of even smaller entities known as quarks. This discovery revolutionized our understanding of the subatomic world. Scientists identified 6 distinct types of quarks, grouped into 3 families. The lightest are the up and down quarks, followed by the charm and strange quarks, and the heaviest are the top and bottom quarks. The diversity of particles detected in experiments can be explained by the combinations of these quarks. For example, protons are formed from 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. The myriad of combinations, such as 3 up quarks forming a delta plus particle or a charm quark paired with an anti-down quark creating a D plus particle, reflects the remarkable complexity of the subatomic world. In addition to quarks, the Standard Model includes leptons, particles such as the electron and muon, along with heavier cousins like the tau and the enigmatic neutrinos, which are ghostly particles that interact only through the weak force. Each type of electron is accompanied by its corresponding neutrino, illustrating that the fundamental structure of reality consists mainly of electrons and up and down quarks. Interestingly, these fundamental constituents of matter appear to lack any size. They are considered point-like particles, leading to the conclusion that protons and neutrons are effectively empty at the subatomic level. This realization adds another layer of complexity to our understanding. The atoms that compose all matter are even more vacant than previously assumed, rendering the concept of solidity an illusion. As you reflect on the apple sitting on your kitchen counter, the notion of it being primarily empty space is disconcerting. Initially, the electrons and nucleus seemed like solid components. However, in the quantum world, particles defy our conventional understanding. What we once believed to be discrete particles have proven to exhibit wave-like behavior, existing in a spread-out form over space rather than occupying precise locations with well-defined properties. In essence, the apple is a combination of these strange quantum waves converging to create the familiar fruit you recognize. Consider your kitchen once more. Picture yourself preparing to bake a cake, referencing a recipe that calls for a couple of eggs. When you open the fridge, the eggs are neatly arranged in their designated spots. You close the door, confident that they will remain in their respective places. Yet, when we apply the principles of quantum mechanics to particles like electrons, we find that certainty is a mere illusion. Electrons cannot be described by the rigid rules of classical physics. Instead, they exist in probabilities. We can no longer speak of electrons as having fixed positions and velocities. Rather, we can only discuss the likelihood of locating an electron in one place or another. If we observe an electron in a specific position, it carries a probability of being found in other locations as well. This means that, at any moment, an electron could tunnel into a new spot, leading to a situation where electrons seemingly exchange places. Why then, one might wonder, do the eggs in your fridge not hop between their slots in a similar manner? While it's true that everything, including eggs, is governed by the laws of quantum mechanics, the probability of an egg quantum jumping from one hole to another is so incredibly minuscule that it becomes practically inconceivable. Within the realm of physics, however, anything is possible, and the quantum world operates on probabilities rather than certainties. The quantum revolution swept through the physics community in the early 20th century, captivating brilliant minds worldwide. Yet, not everyone was enamored by this new perspective, including perhaps the greatest physicist of them all, Albert Einstein. The tension between classical physics and the emerging quantum theories came to a head in 1926 when physicist Max Born published a paper building on Erwin Schrödinger's earlier work. Schrödinger had introduced his famous wave equation, which described the behavior of quantum particles, but he struggled to interpret what these waves truly represented. Born provided clarity by suggesting that these waves should be viewed as waves of probability. The amplitude of a wave function would indicate the likelihood of finding an electron in a given location. Over time, as conditions change, this wave function oscillates, reflecting the shifting probabilities of an electron's location. This framework answered a fundamental question that had long puzzled physicists. In experiments, they would detect electrons as distinct particles, yet simultaneously, these same electrons behaved like waves. Born proposed that while particles like electrons do behave like waves during their journey, the act of detection collapses the wave function, pinpointing the electron to a specific location. The experimental validation of this idea came swiftly. scientists sought to recreate Young's famous double-slit experiment, which demonstrated the wave nature of light. They fired a beam of electrons toward a nickel target, anticipating that if electrons behaved as discrete particles, they would ricochet randomly off the target's atoms. However, the results revealed unexpected patterns of electron recoil. Some directions showed a preference for electrons to scatter, while others seemed to repel them, forming a distinct interference pattern indicative of wave behavior. To visualize this, imagine yourself as an Olympic sharpshooter, zeroing in on a target 100 meters away. As you line up your crosshairs, you take a deep breath and release the shot. The electrons, much like your bullet, are expected to follow a straightforward path. Yet, the interference patterns that emerged suggest a more intricate reality, one where the rules of classical physics falter, revealing a world governed by probabilities and the peculiarities of quantum mechanics. Through these experiments, scientists illuminated the strange nature of the subatomic world. The line between particle and wave has blurred, leading to a rich tapestry of understanding that defies our everyday experiences. The realization that the fundamental constituents of reality behave unpredictably opens new avenues for exploration and deepens our understanding of the universe. This strange new landscape challenges our notions of existence, urging us to reconsider what we define as solid, real, or even knowable. In this quantum realm, the familiar becomes unfamiliar, and the rules we once held dear are reshaped, allowing for the possibility of wonder and discovery that lies just beyond the horizon of our current understanding. Imagine yourself as a sharpshooter, not just any sharpshooter but one operating in the bizarre quantum world. Here, the laws of everyday physics dissolve into a pool of uncertainty, where exact locations and velocities give way to probabilities. When you pull the trigger, the bullet that leaves the barrel does not travel in a straight line. Instead, it manifests as a quantum wave, spreading out in all directions, similar to ripples radiating across a pond. This wave behaves quite differently from the expected trajectory of a bullet. Quantum waves can diffract around obstacles and interfere with each other. If you were to fire a barrage of quantum bullets at a target, the outcome would not be a straightforward array of holes, as one might expect. Instead, you'd see an intricate pattern of interference where some regions are densely populated with hits while others remain completely empty. This duality of waves and particles lies at the heart of quantum mechanics, a phenomenon that continues to puzzle physicists and challenges our understanding of the physical world. While it's strange that we don't experience this duality in our daily lives, experiments have confirmed its existence even at the level of large molecules made up of many atoms. These molecules can travel together as a quantum wave and demonstrate interference patterns, proving that quantum mechanics isn't limited to tiny particles. In various experiments, as Max Born had suggested, the waves representing electrons combine and cancel one another, while detectors count individual electrons arriving at their destinations. The particles, like electrons, travel as waves yet interact with detectors as solid entities. Interestingly, This principle is applied in some of the most advanced microscopes we have today. Instead of illuminating a sample with a beam of light, these devices focus beams of electrons onto a target. By harnessing the wave properties of the electrons, scientists can uncover details far beyond what visible light can reveal. Max Born was awarded the Nobel Prize in Physics in 1954, a year before Albert Einstein's passing. However, in the intervening decades, a rift had developed between these two titans of science. Einstein became increasingly vocal about his skepticism regarding this probabilistic view of nature. He held a conviction that the universe must possess an underlying determinism, a deeper truth that transcended the seemingly random outcomes dictated by quantum mechanics. Though Einstein and Born maintained a friendship, they remained at odds regarding the nature of reality. Einstein found the idea of chance lurking at the foundation of our existence intolerable. He believed the universe should adhere to deterministic principles and that the apparent randomness of quantum mechanics hinted at something deeper and more structured, hidden beneath the surface. In a now famous letter to Born, Einstein expressed his sentiment, stating, "I at any rate am convinced that God does not play dice." By 1935, having fled Germany due to rising political tensions, Einstein began outlining a thought experiment that highlighted what he saw as the absurdities inherent in quantum mechanics. This thought experiment would evolve into a paradox known as the EPR paradox, named after Einstein and his colleagues Podolsky and Rosen. The paradox aimed to illustrate the apparent instantaneous collapse of quantum probability waves into defined particles upon observation. To understand the implications of the EPR paradox, let's consider two quantum particles created together. Unlike classical systems, the wave function governing these particles cannot simply be understood as the sum of their individual wave functions. Instead, a new wave function must be constructed that encompasses the properties of both particles, leading to intricate correlations that leave Einstein puzzled. Imagine that these two particles emerge from an event, perhaps through the annihilation of a photon. Upon their creation, they possess entangled quantum values, such as spin. Suppose one particle spins upwards while the other spins downwards. The total spin remains zero, a conservation that holds true in their creation. However, the wave function does not provide concrete information about their states. Instead, it presents probabilities. Each particle has a 50% chance of being in either spin state, and we remain uncertain about their orientations until we measure one. As they separate and traverse vast distances, perhaps even light years apart, the two particles exist as probability waves, maintaining their uncertainty. This phenomenon is what physicists refer to as quantum entanglement. Now, if one of these particles encounters a spin detector and registers a spin-up reading, the wave function collapses, revealing that the other particle must be spinning downwards. This situation introduces a perplexing dilemma. How do these two distant particles communicate their states? When the first particle's spin is determined, how does the second particle instantaneously know its own spin state? Einstein raised concerns that if the wave function collapses across such distances, it implies information is traveling faster than the speed of light, a violation of one of the fundamental principles of physics. To Einstein, this suggested that quantum mechanics could not provide a complete description of reality. He proposed that beneath the apparent randomness of quantum phenomena lay hidden variables, definitive and deterministic values that would provide a true account of the universe's mechanics. This pursuit of hidden variables captured Einstein's imagination, and he continued to explore this idea throughout his life. Despite Einstein's efforts, the search for hidden variables faced numerous challenges. Theoretical physicists like de Broglie made initial strides, but ultimately abandoned the quest. Others tried to reconcile the EPR paradox, attempting to reintroduce determinism into quantum mechanics. However, by the 1960s, a groundbreaking breakthrough emerged from the work of John Stuart Bell, an Irish physicist stationed at CERN in Switzerland. Bell's contributions to physics are often encapsulated in what is now known as Bell's inequalities. His thought experiment echoed the EPR paradox but added a clever twist that would help reshape our understanding of quantum mechanics. Just like in the EPR scenario, Bell proposed creating entangled particles, allowing them to travel apart before encountering detectors. These detectors could be aligned in various orientations, measuring the particle's spins, either up or down. Bell's inequalities demonstrated that if hidden variables existed, the statistical results of measuring these particles would adhere to certain limits. However, if quantum mechanics was fundamentally probabilistic, then the outcomes would defy those limits, revealing a tension between classical intuitions and quantum reality. This groundbreaking insight led to a series of experiments testing Bell's inequalities, ultimately supporting the probabilistic view of quantum mechanics. As experiments consistently aligned with Bell's predictions, the notion of hidden variables began to wane, leaving physicists to grapple with the implications of a reality governed by probabilistic laws. The quantum world operates on principles that transcend classical intuitions, challenging our understanding of existence itself. This journey through the world of quantum mechanics highlights not only the beauty of its complexity but also the depth of human curiosity and inquiry. As we continue to delve into the enigma of quantum reality, we are reminded that the universe is far stranger than we can imagine, urging us to expand our thinking and embrace the unknown. If you're enjoying this audiobook and finding value in the content, we kindly ask you to take a moment to subscribe to the channel. A large portion of our listeners and viewers haven't subscribed yet, and by doing so, you'll help us grow and continue bringing you more high-quality audiobooks. Your support means a lot to us, and it's just one click away. So, go ahead and hit that subscribe button to stay connected and never miss out on our latest releases. In the enigmatic world of quantum mechanics, one finds themselves grappling with phenomena that challenge the very foundations of classical physics. Imagine you are a sharpshooter aiming at a target with a quantum twist. When you fire, your bullet transforms into a quantum wave, scattering in multiple directions like ripples on a tranquil pond. This wave behaves in ways that defy traditional understanding. It can diffract around corners and interfere with other waves. Instead of hitting the target in predictable patterns, your quantum bullets yield intricate interference patterns, with certain areas filled with marks and others completely barren. This dual nature of matter, where particles can behave like waves, captures the essence of quantum mechanics and raises profound questions about our understanding of reality. Max Born, a pivotal figure in this field, pointed out that the waves of electrons combine and cancel in ways that contradict classical expectations, leading to the intriguing concept of wave-particle duality. This means that while quantum objects exhibit wave-like behavior during travel, they interact as discrete particles upon measurement. The implications of Born's work ripple through modern science, especially in the realm of electron microscopes, which utilize beams of electrons instead of light. These microscopes exploit the wave properties of electrons, allowing scientists to observe details smaller than what light can reveal. The contributions of scientists like Born helped solidify the understanding that reality at the quantum level is far from intuitive. However, not all physicists embrace these probabilistic interpretations. Albert Einstein, a contemporary of Born, found himself increasingly at odds with the prevailing quantum framework. Although he and Born maintained a cordial friendship, they fundamentally disagreed on the nature of reality. Einstein was deeply troubled by the idea of inherent randomness in the universe, believing that a deterministic foundation underpinned all phenomena. He famously expressed his doubts in a letter to Born, asserting, "I at any rate am convinced that God does not play dice." By the mid-1930s, Einstein had fled his native Germany, seeking refuge in the United States, where he began formulating a thought experiment that would challenge the very essence of quantum mechanics. This thought experiment gave rise to the EPR paradox, named after its creators, Einstein, Podolsky, and Rosen. The paradox sought to highlight the oddity of quantum mechanics, particularly the instantaneous collapse of probability waves into distinct particles upon observation. To appreciate the EPR paradox, consider two quantum particles born together through an event. These particles possess entangled properties, meaning that their quantum states are intertwined. For instance, imagine they are created with spins that are oppositely aligned, one spinning up and the other spinning down. Although the wave function describes their states in terms of probabilities, the total spin remains conserved. If one particle is measured to be spinning up, the other must be spinning down. As these particles drift apart, perhaps over light years, their individual states remain uncertain, an essence of quantum entanglement. Yet, when one encounters a spin detector that reads spin up, the wave function collapses, and the other particle must instantly assume a spin-down state. This leads to a perplexing question: how do these distant particles communicate their states? Einstein argued that if this instantaneous collapse were true, it would imply information travels faster than light, a notion he vehemently rejected. Einstein posited that quantum mechanics could not fully describe reality as it stood. He believed that beneath the randomness of quantum interactions lay hidden variables, definite parameters that could explain the nature of reality in deterministic terms. This quest for hidden variables became Einstein's intellectual pursuit, leading to a lengthy debate within the scientific community. Yet, the search for these hidden variables faced significant challenges. Some theorists, including de Broglie, initially explored potential solutions but eventually abandoned the pursuit. However, the landscape of quantum mechanics began to shift with the advent of John Stuart Bell, an Irish physicist whose work would redefine our understanding of quantum correlations. Bell's work led to the formulation of Bell's inequalities, a pivotal concept that would test the validity of hidden variable theories. In his thought experiment, he considered entangled particles, allowing them to separate before encountering detectors that could measure their spins. Bell's twist involved altering the alignment of these detectors, creating various configurations to probe the nature of correlations. Imagine one detector measuring up and down, while the other measures left and right. This setup may seem nonsensical, as one might think a particle can only spin in one direction at a time. However, quantum particles defy such classical logic. They exist in a realm of probabilities, allowing for unexpected correlations that challenge our understanding of reality. As Bell conducted his experiments, he anticipated distinct patterns of correlations based on the existence or absence of hidden variables. If hidden variables defined reality, specific correlations should emerge. Conversely, if quantum mechanics operated purely on probabilistic principles, a different pattern would surface. This drove physicists to undertake a flurry of experiments to validate Bell's hypotheses. The first significant results came when physicists excited calcium atoms in a heated oven, producing two correlated photons that emitted light. As these photons traveled toward detectors, scientists compared their polarizations, probing the vibrational direction of their electric fields. Bell predicted that hidden variables would yield specific correlations, while a probabilistic approach would yield a distinct set of outcomes. The results of these experiments were revelatory. They indicated the absence of hidden variables, supporting a non-local view of reality. The implications of these findings are profound, as they challenge the classical notion of locality, the idea that an object is influenced solely by its immediate environment. Einstein had resisted this concept, coining the term spooky action at a distance to describe the perplexing nature of quantum entanglement. For him, the idea that distant particles could influence one another seemed unacceptable. Yet, the experimental evidence consistently pointed to a reality that was fundamentally non-local. This realization reshaped our understanding of the universe. It suggested that fundamental particles do not exist as isolated entities, rather, they are interconnected across vast distances. Each electron, quark, and photon may share a cosmic bond that transcends classical definitions of separation. This interconnectedness implies that no particle is entirely independent, all are woven into the fabric of the universe. At this juncture, one might share Einstein's unease with such a radical notion. The idea that an apple sitting on a table is entangled with particles light years away stretches the boundaries of intuition. However, it is crucial to acknowledge that the universe operates independently of human perception and logic. The cosmos adheres to its own principles, which may defy our expectations. The absurdity of this reality was underscored in 2022 when the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their groundbreaking work on entangled photons. Over decades, these physicists demonstrated that widely separated particles could behave as a unified system, reinforcing the non-local nature of reality. Their experiments dismissed the notion of hidden variables and reaffirmed the idea that reality operates beyond the confines of classical intuition. A recent example, the cosmic bell test, pushed the boundaries of understanding further. Concerns arose that experimental results might not accurately reflect true correlations due to the entangled nature of the experimental apparatus itself. Physicists often assume they are objective observers, insulated from the very particles they study. However, the atoms composing their bodies and instruments carry histories that extend far back in time, raising questions about the integrity of measurements. To circumvent these potential biases, physicists turn their gaze to the cosmos. They harness the light from distant stars, using its fluctuations to influence the settings of their experiments. This celestial approach aimed to eliminate any terrestrial influences that could skew results. Remarkably, experiments using quasar light, originating billions of years ago, yielded unequivocal evidence: reality must be non-local. The discoveries stemming from these experiments compel us to reconsider our understanding of reality. As you observe your apple, it's worth pondering that beneath its seemingly mundane surface lies a connection to a vast universe, a universe where entanglement and non-locality shape the very essence of existence. In this quantum realm, reality transcends classical boundaries, urging us to embrace a more expansive view of the cosmos. In the intricate tapestry of the universe, each fundamental particle plays a crucial role, almost as if it were a small piece of fruit in a cosmic orchard. You might think that the electrons and quarks, with their well-defined characteristics, exist independently. However, a deeper inspection reveals a surprising truth: these particles are not isolated, they are entangled in a complex web of connections with each other and the universe at large. This interplay raises profound questions. Why is this apple, or any particle, so intimately tied to the cosmos? What underlying rules govern these relationships? On April 18, 1955, the world bid farewell to one of its greatest scientific minds, Albert Einstein. Born in Germany nearly 8 decades earlier, his last moments were spent in an American hospital, surrounded by the aura of curiosity that had defined his life. Though his final words were lost to history, he requested his glasses, writing materials, and equations, hoping to solve one last problem before departing this realm. Einstein's legacy continues to reverberate through modern physics, but by the end of his life, he was fixated on a singular question that still occupies physicists today. The early decades of the 20th century saw the emergence of two monumental theories that reshaped our understanding of the cosmos: Einstein's theory of relativity and the burgeoning field of quantum mechanics. While relativity elegantly described gravity's influence across vast distances, quantum mechanics delved into the enigmatic world of subatomic particles. Over time, quantum mechanics evolved into quantum field theory, QFT, which characterizes the fundamental particles, like electrons and quarks, as excitations in underlying fields. These fields ripple through space, conveying the probabilities that govern the behavior of particles. At the heart of quantum field theory lies the Standard Model of particle physics. This framework delineates the interactions between different quantum fields. For instance, when charged particles such as electrons interact, they create disturbances in the electromagnetic field. These disturbances manifest as photons, the carriers of electromagnetic force. Similarly, electrons are excitations within the electron field, while quarks, which comprise protons and neutrons, arise from their own respective fields. Beyond these, various fields correspond to the fundamental forces governing the universe. The strong force, for example, is responsible for binding quarks together within protons and neutrons, with gluons serving as its carriers. The weak force plays a crucial role in radioactivity, its particles known as W and Z bosons facilitating certain transformations in particles. Each force, each interaction, and each particle can be understood through the vibrations in their respective fields. Consider the life of a neutron, which serves as a compelling example. A free neutron, left to its own devices, has a relatively short lifespan of about 15 minutes before it decays into a proton, emitting an electron and a ghostly neutrino in the process. At a quantum level, this decay reflects the interplay of fields. A neutron is composed of 3 quarks, 2 down quarks and 1 up quark, constantly generating vibrations in the strong force field through the exchange of gluons. Eventually, a down quark undergoes a transformation facilitated by the weak force, becoming an up quark and thereby transforming the neutron into a proton. This interaction releases a W- boson, which itself exists for an incredibly brief moment before generating further vibrations in other fields, creating an electron and a neutrino. These interactions exemplify how quantum processes govern the behavior of particles, and every particle transformation can be explained in this framework. But there is one more significant field we must consider: the Higgs field. The interactions with this field give mass to fundamental particles, with the Higgs boson being its vibrational manifestation, a particle discovered in 2012 after decades of rigorous searching. In the early 1960s, physicists confronted a conundrum. The weak forces W and Z bosons possessed mass, while other force carriers, like photons and gluons, remain massless. The mathematical formalism of quantum field theory dictated that all force particles should be massless, and merely introducing mass to the W and Z bosons resulted in chaotic infinities within the equations. Thus, a novel mechanism was needed to incorporate mass without derailing the entire framework. This was where the Higgs field stepped in. The Higgs field, an omnipresent energy field, grants mass to the W and Z bosons through a unique coupling mechanism. Photons and gluons, however, remain unaffected by this field, explaining their massless nature. The beauty of the Higgs mechanism lies in its capacity to bestow mass upon all fundamental particles. As electrons and quarks traverse the seemingly empty void of space, the Higgs field interacts with them, ensuring they possess the correct mass essential for the structure of the universe. Quantum field theory stands as a powerful tool, accurately predicting outcomes in particle experiments and accounting for the myriad particles we observe: electrons, quarks, and sprays of gluons. Similarly, Einstein's theory of relativity excels in predicting celestial motions. However, therein lies the source of Einstein's frustration. Despite their remarkable success, the two theories operate in fundamentally different languages. Einstein's relativity speaks of gravity through the curvature of spacetime, while quantum field theory articulates the universe in terms of probabilities and wave functions. You may wonder why the distinction matters, but for physicists like Einstein, the existence of two incompatible frameworks contradicted the ultimate aspiration of modern physics: unification. This dream of unification has deep historical roots. It began with James Clerk Maxwell's groundbreaking work on electromagnetism, which synthesized electricity and magnetism into a single framework. As quantum field theory advanced, it began to encompass three of the fundamental forces: electromagnetism, the strong force, and the weak force. Physicists longed for a coherent mathematical description that could reconcile these disparate phenomena. Yet, challenges persisted. The question loomed: how could these two distinct frameworks, one describing gravity and the other governing quantum interactions, be harmonized? Physicists explored various paths, searching for a theory of everything that could encapsulate all known forces and particles within a single framework. The quest for unification became the holy grail of theoretical physics, spurring numerous investigations and advancements. In this ongoing pursuit, scientists began to investigate the very fabric of space-time, delving into theories that bridge the gap between quantum mechanics and general relativity. Approaches such as string theory and loop quantum gravity emerged, seeking to unify these realms. While these endeavors remain speculative and far from definitive, they exemplify humanity's relentless curiosity and drive to understand the cosmos. So, as you gaze at your apple or ponder the intricate web of fundamental particles, remember that what appears solid is merely a facade, a manifestation of an underlying reality defined by probabilities, fields, and intricate interactions. The universe thrives on connections, and the quest to comprehend these connections fuels the ongoing exploration of physics. Ultimately, the search for unification continues, promising to unveil the profound truths that govern our existence and revealing that the apple, and indeed everything around us, shares an intrinsic bond with the cosmos. The quest for a unified theory of physics has long been a fundamental pursuit for scientists. Many phenomena, seemingly unrelated, have found their places within coherent frameworks, except for gravity, which stubbornly resists such neat categorization. The dawn of general relativity in the early 20th century ignited curiosity among physicists about the existence of extra dimensions, prompting them to wonder whether our familiar spacetime could conceal additional dimensions that might account for gravity and the electromagnetic force. This idea appeared to offer potential solutions, albeit imperfect ones. The glaring question remained: where are these extra dimensions? Surely, if there were more than the three dimensions of space, up, down, left, right, forward, backward, we would notice their presence. Physicists proposed a fascinating hypothesis. What if these dimensions were curled up so tightly that they eluded our perception? It was akin to a puzzle box, where each piece is part of a larger structure, yet remains hidden from view. For decades, this concept languished in the shadows until the 1960s, when a resurgence of interest breathed new life into the idea of curled dimensions. Physicists began to entertain the revolutionary notion that fundamental particles might be better described not as discrete points but as loops of string. Thus, the string theory revolution began. Throughout the 1980s and 90s, physicists believed they were on the verge of a breakthrough. They thought that with just the right mathematical formulation, everything would fall into place. However, as they grappled with the complexities of the 20 or more dimensions needed to support the theory, the unification of physics seemed to drift further from reach. Over time, string theory evolved into what is known as M-theory, a name given by its originator, Edward Witten, reflecting an openness to new interpretations of the theory. In this framework, strings have been replaced by membranes, leading to even more complex mathematical structures. Despite the promise, M-theory currently exists more as a collection of ideas than a fully formed theory seeking unification. Not all physicists have embraced string theory. Some have pursued alternative paths, seeking different mathematical structures that could provide a foundation for understanding reality. Loop quantum gravity, for instance, attempts to construct reality from fundamental units of space and time. Yet, like string theory, it has presented formidable mathematical challenges and has yet to establish itself as a unifying theory. In this ongoing search for a grand theory of everything, new mathematical concepts are constantly proposed and tested. Most of these ideas eventually face rejection, but they help guide the exploration. A key concept in this pursuit is symmetry, a principle that approaches the essence of the universe's fundamental rules. Symmetry is not just an aesthetic consideration, it is a powerful tool in physics. When we think of symmetry, we often envision pleasing shapes, like a perfectly balanced vase or a well-proportioned building. However, symmetry can also be understood through mathematics. The presence of symmetries has a profound impact on the nature of reality. Take a sphere, for instance, a shape that mathematicians can define with precision. When you rotate a sphere, it retains its appearance. It has what we call rotational symmetry. This quality is not merely visual, it allows physicists to investigate similar symmetries throughout the fabric of physics. Emmy Noether's groundbreaking work in 1915 established a vital connection. Every symmetry corresponds to a conservation law. But what does this mean in practical terms? Imagine conducting a physics experiment involving rolling balls down a slope and measuring their speeds. If you were to shift the entire setup 1 meter to the left or right and repeat the experiment, you would likely expect the same results. This consistency reflects a symmetry, implying that the outcome remains unchanged regardless of spatial translation. Noether's mathematics tells us that the conserved quantity here is momentum, the product of mass and velocity. Momentum cannot simply vanish during interactions. One billiard ball transferring energy to another illustrates this principle in action. Other symmetries exist and give rise to additional conservation laws. If you rotate your experiment by 90 degrees and repeat the rolling of the balls, you again expect the same outcome. Here, the conserved quantity is angular momentum, representing the conservation of spin in the universe. The concept of time symmetry is perhaps the most intriguing. If you conduct your experiment today and repeat it tomorrow, you would expect similar results. This time symmetry implies the conservation of energy, indicating that energy cannot be created or destroyed. Symmetries permeate theoretical physics. Einstein's special relativity is fundamentally grounded in symmetries, derived from what is known as the Lorentz group of symmetries. These symmetries dictate that the speed of light is the ultimate speed limit in the universe. Yet, it is in quantum mechanics that symmetries truly flourish. Physicists discover that electromagnetism exhibits a symmetry referred to as U1, while other symmetry groups describe the strong and weak forces. Each symmetry group introduces new conserved quantities. In electromagnetism, charge is the conserved quantity, whereas in the context of strong and weak forces, other quantum numbers emerge. These may include isospin, lepton number, quark numbers, and various others, forming a rulebook of reality that delineates permissible interactions. If conservation laws hold, interactions can occur. If broken, they become strictly forbidden. As physicists delve deeper into the nature of reality, they have sought to incorporate increasingly complex symmetries, leading to the concept of supersymmetry. This theory posits that every fundamental particle in the Standard Model should have a superpartner, a mirror counterpart. For instance, for every electron, there should exist a selectron, for every photon, a photino, and so on. Supersymmetry aims to enhance the mathematical elegance of the Standard Model and may even offer pathways to deeper insights into the universe. However, the absence of experimental evidence for supersymmetric particles has led many to declare the concept a dead end. Symmetries also play a central role in string theory and M-theory, where different symmetry groups are employed to clarify the complexities of the frameworks. Clues continue to arise from geometry and symmetry, leading many physicists to invest their hopes in what is termed the ADS/CFT correspondence. This concept, identified by Argentine physicist Juan Meldacena in the late 1990s, establishes a mathematical mapping between aspects of string theory that includes gravity and particle theories without gravity. Essentially, it suggests that the mathematics of a particular four-dimensional universe, one governed by quantum mechanics alone, could parallel that of a five-dimensional universe with gravity. The exploration of symmetries and their implications forms a cornerstone of the ongoing quest for unification in physics. As researchers continue to navigate the complexities of the universe, the interplay between fundamental particles and their governing forces remains a captivating endeavor, promising new insights into the profound nature of reality itself. At its core, the relationship between gravity and quantum mechanics presents a fascinating puzzle for physicists, suggesting a profound mathematical connection between these two realms. Countless hours of research have been dedicated to unraveling the intricacies of this relationship, which might lead us to a deeper understanding of a unifying theory of everything that governs our reality. One significant development in this ongoing exploration is the ADS/CFT correspondence, a concept that carries intriguing implications. Imagine an optical hologram, where a three-dimensional image is encoded onto a two-dimensional surface. One potential takeaway from the ADS/CFT correspondence is the idea that our reality might similarly be a projection of information, with the essence of our experiences emerging from lower-dimensional data. This notion, known as the holographic principle, stemmed from advancements in black hole physics. Black holes, remarkable in their simplicity, are defined solely by three properties: mass, angular momentum, and charge. They seem to completely forget the identity of anything that falls into them. The implication is that all information except these three defining traits is lost. In the realm of physics, however, it is generally accepted that information cannot be created or destroyed, only transformed from one state to another. This raises an intriguing problem. Where does the information about matter that enters a black hole go? Initially, it was proposed that this information resides deep within the black hole itself, concealed from the external universe. Yet, in the 1970s, the groundbreaking work of physicist Stephen Hawking shattered this notion. He posited that quantum effects near a black hole's event horizon lead to the emergence of particles from the turbulent quantum vacuum. These particles escape into the universe, seemingly taking energy away from the black hole and resulting in a gradual decrease in its mass until it eventually evaporates completely. However, if a black hole's information were indeed contained within it, what happened to that information as it evaporated? It became clear that the ejected particles did not carry this information. Thus, physicists began to seek an alternative explanation. One suggestion was that the information was not captured within the black hole itself but instead encoded on its event horizon. As matter falls into the black hole, the information could imprint itself on the horizon, later transferred to the escaping particles during evaporation. In this model, black holes are viewed as three-dimensional objects existing in three-dimensional space, while the information they contain resides on a two-dimensional surface, the event horizon. This aligns closely with how a hologram encodes three-dimensional images within a two-dimensional plane. Intriguingly, some physicists propose that the entire universe may operate under similar principles, where our three-dimensional experience is an intricate projection stemming from lower-dimensional data. Before we delve deeper into the implications of symmetry in physics, it is crucial to recognize that these symmetries cannot be entirely flawless. Some must exhibit imperfections or cracks, as a completely symmetric universe would render our existence impossible. A prime example of this is the observed asymmetry of matter in the cosmos. Our universe is filled with electrons, many of which orbit atoms, while their antimatter counterparts, positrons, are exceedingly rare. In the Milky Way, scientists estimate that positrons account for no more than a quadrillionth of the matter present. This prompts a vital question: where have all the positrons gone? The answer lies in another symmetry consideration. In the universe's early moments, during the formation of matter, a purely symmetric process would have produced equal quantities of matter and antimatter. For every electron created, a positron would have emerged, leading to their mutual annihilation and leaving behind only radiation. Without this matter, there would be no atoms, no stars, no planets, and no people, just a featureless void. For matter to exist, there must have been a break in the symmetry of matter creation, an infinitesimal asymmetry on the order of 1 part in a billion that allowed for the existence of one electron for every billion annihilations. Similarly, protons must outnumber antiprotons, and neutrons must dominate over antineutrons. This asymmetry provides the matter that composes our world, but physicists have yet to pinpoint where this break occurs within their theoretical frameworks. A theory of everything may be required to reveal the nature of this phenomenon fully. Beyond the asymmetry in matter creation, other imbalances in symmetry may offer clues regarding the underlying fabric of reality. A notable player in this scenario is the weak force, the most peculiar of the fundamental forces. Unlike the other forces, the weak force distinguishes between matter and antimatter. To illustrate this, consider a hydrogen atom, composed of a positively charged proton at its nucleus, orbited by a negatively charged electron. When this electron transitions between orbits, it absorbs or emits light in a specific pattern. Now, consider an antihydrogen atom, which consists of a negatively charged antiproton surrounded by a positively charged positron. When the positron transitions in its orbit, it produces a similar pattern of light. This mirrors what is observed with normal hydrogen, demonstrating that electromagnetism exhibits symmetry regarding matter and antimatter. The same holds true for the strong force and even gravity. However, the weak force defies this trend. Reactions influenced by the weak force yield different outcomes depending on whether they involve matter or antimatter. This phenomenon is intricately connected to one of the universe's most enigmatic particles, the neutrino. Neutrinos interact solely via the weak force, positioning them as essential players in weak interactions. An intriguing aspect of neutrinos is their fundamental property: they all spin in the same direction. This quantum characteristic of spin exists in quantized units, meaning they cannot have arbitrary values. In summary, the interplay between gravity and quantum mechanics reveals a complex web of relationships that may hold the key to a deeper understanding of the universe. The holographic principle suggests that our reality could be a projection of lower-dimensional information, while the observed asymmetries challenge our comprehension of fundamental forces. The weak force's unique behavior further complicates our understanding of matter and antimatter, making the quest for a comprehensive theory of everything an ever-evolving journey in modern physics. As scientists continue to explore these profound questions, the convergence of gravity, quantum mechanics, and the nature of reality promises to shed light on the mysteries that lie at the heart of existence itself. In the realm of quantum mechanics, particles exhibit intriguing properties that often defy common sense. Consider photons, the fundamental particles of light, which possess a property known as spin. This spin can be likened to a directional twist, right or left-handed, as these photons travel through the universe. While both types can coexist, neutrinos, on the other hand, present a striking contrast. All neutrinos are left-handed, while their counterparts, the antineutrinos, are right-handed. This distinction introduces a unique dynamic into the interactions between matter and antimatter. The reason for this left-right differentiation in neutrinos and the weak force remains an enigma. Physicists are still grappling with this fundamental question. What we do know is that this apparent crack in the fabric of reality has played a crucial role in ensuring our existence. Without this asymmetry, matter and antimatter would have obliterated each other in the initial moments of the cosmos. Our journey through understanding the rules governing reality has taken us through a myriad of concepts: quantum fields, broken symmetries, and warped spaces. Yet, there exists one final illustration of the peculiarity that arises when we delve deep into the quantum realm. When you gaze up at the night sky, the light from distant stars reaches your eyes, where it is detected by electrons. These electrons engage in a delicate dance, exchanging photons with those emitted from stars millions of light years away. To experience the electromagnetic force, two electrons must vibrate within the photon field, creating a bridge of communication. But how do these electrons decide to engage in this exchange? One might think that a single electron emits a photon that randomly interacts with another, but this isn't how quantum mechanics operates. For a photon to be exchanged, there must be mutual agreement. One electron must emit, while another must absorb. This seemingly paradoxical interaction is captured in the transactional interpretation of quantum mechanics. In this view, the electrons initiate a sort of handshake, a temporal agreement, facilitating the exchange of photons. One electron sends its handshake into the future, while the other sends its response into the past. This mutual agreement allows photons to be exchanged, even across vast distances of billions, or even trillions, of light years. However, the idea that time travel plays an intrinsic role in reality can be unsettling for some. Critics may dismiss this as a mere mathematical convenience, masking a more profound truth about the universe. This leads us to contemplate where we stand in our understanding of reality. From holographic universes to the implications of abstract mathematics, we find ourselves teetering on the philosophical brink of science. What, then, is the essence of science? Is it a relentless pursuit of truth aimed at uncovering the ultimate nature of reality? Or is it merely a series of mathematical approximations that hint at a reality forever hidden from our perception? These thoughts can leave us in a whirlpool of confusion, only to be interrupted by an urgent inquiry. If nothing is real in a concrete sense, then what exactly are you? This question resonates with a thought-provoking ancient Greek legend, the ship of Theseus. Over the years, the ship undergoes extensive repairs and maintenance, with every plank, nail, and piece of sail eventually replaced. Philosophers have pondered whether this vessel, devoid of any original components, remains the ship of Theseus. If not, at what moment did it cease to be the original ship and transform into something else? This inquiry may seem trivial, rooted in philosophical abstraction, but it carries profound implications about the nature of reality and identity. Consider your own existence. How old are you, really? If you were to cut yourself, fresh, vivid red blood would flow from the wound. But is this blood the same as the blood coursing through your veins in childhood? The lifespan of a red blood cell is a mere 4 months. Every second, approximately 5 million red blood cells perish, making way for new ones. This means your body undergoes a complete replacement of blood 3 times each year. Most of your body is subject to this cycle of renewal. Skin cells regenerate every few weeks, while internal organs may take up to a decade to replace. Bones, too, undergo a lengthy regeneration process, lasting around 15 years. With such continual transformation, it's undeniable that you are not the same person you once were. Each of us, in a way, is a biological ship of Theseus. This raises profound questions about identity. Are you still the same you who was born, even though every individual cell has been replaced countless times? Just like the ship of Theseus, when did you transition from the original you to the you that exists today? If you are not the same you, then what defines your identity? The quest to locate the essence of the mind and the seat of consciousness has perplexed thinkers throughout history. For ancient Egyptians, the heart was considered the epicenter of thought and emotion, the dwelling place of the soul, with thoughts emanating to the body's extremities. This conflation of thinking about thought leads to a conundrum. What exactly constitutes a thought? René Descartes ventured into this philosophical territory, positing a separation between the brain and the mind. He invited us to imagine shrinking ourselves to the size of a flea, embarking on a tour of the brain. Here, he suggested, we would find no visible signs of thoughts or ideas, asserting that the mind existed separately from the physical brain. However, in the 20th century, Descartes' dualism faced significant scrutiny. Advances in technology and biological understanding began to challenge the notion of a distinct mind. Real-time mapping of brain activity revealed a complex network of over 80 billion neurons interconnected in an intricate web. This mapping illuminated the electric pulses that characterize thoughts and sensations. The brain pulses with electrical activity, with different areas lighting up in response to various feelings and thoughts. While it might be tempting to perceive thoughts as something mystical or separate from the physical realm, it appears that thoughts emerge from the biological machinery of the brain. This realization reshapes our understanding of consciousness, framing it as a product of electrical signals rather than a mystical entity. Yet, despite these advances, the nature of consciousness remains elusive. What is it that gives rise to subjective experiences? How do these electrical interactions translate into the rich tapestry of thoughts and emotions that define human experience? This profound mystery continues to inspire inquiry, encouraging us to explore the intricate connections between our physical existence and the intangible essence of thought. As we contemplate these intricate ideas, we are reminded of the deep complexity of our universe. From the behavior of fundamental particles to the intricate workings of our minds, the quest for understanding is an unending journey. Each discovery leads us to deeper questions, urging us to explore the nature of existence, reality, and consciousness itself. The intricacies of the human mind present a fascinating yet perplexing landscape. Often described as a web of chaotic electrical signals, the exact mechanisms that underpin our thoughts, feelings, and creativity remain shrouded in mystery. Where do emotions like love reside? What is the origin of our imagination? Understanding the brain is akin to deciphering an enigmatic puzzle, one that even the great mind of Einstein could not unravel completely. Following his death, a renowned autopsy led to the examination of his brain, revealing its structure yet leaving its remarkable capabilities unexplained. The complexity of our neural networks may hint that consciousness and thought are emergent phenomena, properties that arise from intricate systems rather than being simply reducible to their individual parts. This idea of emergence can baffle scientists, as it introduces a layer of understanding that transcends the sum of its components. A vivid illustration of this concept can be drawn from a historical anecdote involving a Soviet aide in the 1980s who visited London. Intrigued by the seemingly efficient production of bread, he sought to find the individual responsible for its organization. In the Soviet model, bread production was tightly controlled, leading to long queues in cities like Moscow. In stark contrast, the Western approach thrived without centralized management, where countless workers independently performed their tasks. This self-organization mirrored the behavior of an ant colony, where thousands of ants operate with apparent purpose yet without a single leader directing their actions. Here, complex systems give rise to emergent behaviors, and the results can be remarkably effective. Emergent phenomena can also be observed in the natural world. Water, for instance, is merely a collection of molecules governed by electromagnetic interactions. Yet, when gathered in a body, water exhibits flowing currents, bubbles, and swirling eddies, dynamic behaviors that arise from simple rules governing the behavior of its molecules. Similarly, the fundamental properties of matter and gases emerge from basic principles. Some scientists even speculate that gravity might emerge from deeper aspects of space and time, just as the properties of water arise from molecular interactions. The realization that the richness of our reality, our thoughts, experiences, and consciousness, might boil down to the result of complex wiring can be both unsettling and hopeful. If consciousness is merely the outcome of intricate systems rather than a mystical force beyond the physical world, could it one day be replicated or even surpassed? This question lies at the heart of artificial intelligence research, where the ambition is to construct ever more complex networks, both virtual and physical, in hopes that consciousness could emerge from these systems. A branch of physics known as synthetic intelligence seeks to explore this very notion. Unlike traditional artificial intelligence, which aims to mimic human thought, synthetic intelligence focuses on building nanowire networks designed to behave like the neurons in our brains. The goal is to create electronic currents that represent thoughts, allowing these networks to reorganize and remember in a manner akin to our own cognitive processes. While such ideas may sound like the stuff of science fiction, we may be on the cusp of creating thinking machines. For those who adhere to Descartes' dualism, believing that consciousness is a separate entity from the physical body, this endeavor may seem futile. They argue that no purely physical mechanism could replicate the depth of human thought. In contrast, proponents of synthetic intelligence maintain that it is only a matter of time and complexity before we develop networks capable of consciousness. Yet, if consciousness is indeed a physical process occurring within the neural structures of our brains, a plethora of deeper philosophical inquiries emerge. Could it be possible that we are merely brains in vats, fed sensory input from a simulated reality? What if we are not physical brains at all but software running on an advanced computer? And what if Descartes' dualism holds true, implying that consciousness exists in a non-physical realm, perhaps in a soul-like essence? This line of questioning leads to another philosophical conundrum. Why should consciousness be confined to human beings? What if consciousness is far more widespread, permeating the universe? The idea of panpsychism, consciousness existing in all forms of matter, has intrigued many philosophers. This view posits that every particle, tree, rock, and even the cosmos itself possesses some degree of consciousness. While philosophers may find this idea alluring, many scientists are reluctant to embrace it. They contend that such notions extend beyond the boundaries of empirical science. Yet, the two groups often fail to engage in meaningful dialogue. So, could it be that everything in existence is conscious? Is reality itself alive? As you ponder this, your scientific reasoning may lead you to conclude that the idea is too far-fetched, prompting you to shift your focus back to a more tangible object, an apple. The apple captures your attention as you reflect on its existence, considering both its physical entirety and its elemental components. As you delve deeper into these thoughts, you can't help but wonder if, in some way, the apple is contemplating your reality, too. The curiosity that follows can lead to a spiral of increasingly bizarre thoughts about existence and consciousness. Of course, the questions can become even more perplexing when you consider the archetype of the scientist. What image comes to mind? For many, it might be the familiar, wild-haired visage of Albert Einstein, possibly sticking his tongue out, or a younger Isaac Newton adorned in his 18th century regalia. These representations depict scientists long after their groundbreaking discoveries, yet history teaches us that many significant breakthroughs in science occur in youth. Pop culture, particularly shows like The Big Bang Theory, often perpetuates the stereotype of the awkward, young scientist. Indeed, it is essential to remember that Einstein made his pivotal contributions at just 26, while Newton was merely 23 when he unveiled his insights into nature. During the year 1666, a young Newton was studying at the University of Cambridge, yet this period would prove monumental, as the Black Death re-emerged in Britain. The bubonic plague, which had ravaged Europe in the 14th century, had never truly vanished. As it returned in 1666, many fled cities, leading to a rare opportunity for contemplation and reflection among those left behind. This period of isolation provided fertile ground for groundbreaking ideas to flourish. Just as the chaos of a pandemic could lead to unprecedented thoughts and creativity, the quest to understand consciousness and the fabric of reality is far from complete. With questions remaining and ideas evolving, we find ourselves at a nexus of scientific inquiry and philosophical exploration. The interplay of complex systems, consciousness, and the nature of existence beckons us to investigate further. As we continue to explore, the boundaries of what we understand may expand, offering new insights into the enigmatic interplay between the mind and the universe. In this journey, we remain on the precipice of discovery, navigating the uncharted waters of human thought, reality, and consciousness itself. As the plague swept through England, Isaac Newton sought refuge from the turmoil of the world in the serene countryside. Leaving the bustling halls of Cambridge, he retreated to his family's farm in Woolsthorpe, Lincolnshire. There, beneath the shade of a fabled apple tree, he found not only a physical haven but also a mental sanctuary that ignited his curiosity to unravel the mysteries of the cosmos. In this tranquil setting, Newton contemplated the concepts of space and time, delving deeper into the fabric of reality. His groundbreaking equations of motion allowed him to perceive time as a linear continuum divided into three distinct segments: the past, the present, and the future. The past is a closed chapter, the future an unwritten story, and the present a fleeting moment that evolves from what has been and moves toward what is yet to come. In Newton's deterministic universe, everything was calculable. If one possessed complete knowledge at any given instant, they could predict the universe's state at any other point in time, raising a tantalizing question: Has the past truly faded away, and is the future genuinely unknown? In this deterministic model, it might seem that the realities of past, present, and future coexist, with the present merely a sliding window across an already mapped timeline. As if choreographed by an unseen hand, we move through time, momentarily experiencing a singular reality. This idea resurfaced with vigor in Einstein's theory of relativity, which transformed our understanding of time and space. Rather than being mere backdrops, space and time became intertwined, with every particle tracing its own unique path through these four dimensions. Like Newton, Einstein conceived of a universe that was fundamentally deterministic, with past, present, and future all etched into a cosmic ledger. This model, referred to as the block universe, suggests that the entire timeline exists simultaneously, challenging our perceptions of time. In a block universe, knowledge of the future is not shrouded in mystery. Instead, it is as calculable as the past. The mathematical underpinnings of relativity reinforce this notion, suggesting that now must be defined within the broader context of the timeline, making it just one point among many. The implications of a block universe provoke discomfort, particularly concerning the concept of free will. Our innate belief in the ability to choose our paths feels profoundly human. Yet, if the future is predetermined and merely unfolding, then free will might be nothing more than an elaborate illusion. Furthermore, the block universe teeters on the edge of science fiction. If every moment of time exists, could we traverse back to witness history? Picture wandering alongside dinosaurs or witnessing the dawn of humanity. It's an enticing thought, yet the essence of a block universe leaves us feeling detached from the fluidity of time as we experience it. As the conversation around time continued, quantum mechanics emerged as a new contender, proposing a different narrative. Rather than painting a deterministic picture, quantum mechanics introduces a probabilistic nature, suggesting that the future is not strictly defined. Instead of rigid outcomes, the universe is filled with possibilities. This tension between determinism and probability leads us to a nuanced understanding. Perhaps the universe exists as a block, but the present moment is constantly evolving. The present is a dynamic construct built upon the outcomes of quantum possibilities. In this scenario, the past remains fixed behind us while the future stretches ahead, a canvas waiting to be painted by the unfolding present. One intriguing framework that aligns with this notion is loop quantum gravity, a theoretical approach vying for a comprehensive theory of everything. In this view, the universe is woven from fundamental loops of space and time. Now exists at the forefront of this cosmic weaving, with the past forming a tapestry and the future representing an unknown expanse. Our current reality, then, is at the active edge of this creation process. This perspective invites a reconsideration of our grip on reality. Is the apple in your hand the same apple you perceived just moments ago? Are its fundamental properties and timeline in a state of continuous reconstruction? As these profound questions swirl in your mind, the search for reality's true nature becomes more pressing. Could it be that reality is merely the block universe, with free will an illusion? Or perhaps loop quantum gravity offers a more accurate portrayal of existence as an unfolding universe? Yet, what if there's an even deeper foundation beneath reality? What if, at the core, everything is nothing but numbers? This concept is not as far-fetched as it may sound. It resonates with our understanding of the fundamental workings of the universe. At the heart of all physical laws lies the idea of information and information processing. The laws of physics transform our knowledge of a situation, like the position and velocity of a ball in motion, into predictive insights about the future. In quantum mechanics, the information from a scenario is encapsulated within the wave function, evolving as the laws of quantum mechanics unfold. Here, numbers turn into new numbers, with the laws of physics orchestrating this transformative process. By the mid-20th century, profound connections emerged between information and thermodynamics, revealing that processing information demands energy. Whether in a computer flipping a bit from one state to another or in your brain processing even the simplest of thoughts, energy is essential. This realization has led some to propose a radical idea: everything is fundamentally about information processing. There exists no meaningful distinction between processing information on a computer, in our minds, or in the physical realm that constitutes reality. This line of thought gives rise to the simulation hypothesis, the idea that our thoughts, memories, and experiences are mere computations. This hypothesis transcends the notion of being a brain in a vat. It suggests that in our reality, nothing is physical at all. Instead, it raises questions about where these computations exist. Perhaps they unfold in a higher reality, a physical domain beyond our comprehension. This leads to profound inquiries about the purpose of our simulated existence. Why would our creators design a reality for us? What if we are merely characters in a grand game, such as The Sims, with no inherent purpose? This idea propels us into an exploration of existence, questioning the boundaries of our reality. In the midst of these philosophical musings, it becomes clear that our understanding of the universe is both a quest for knowledge and a confrontation with uncertainty. Whether we exist in a deterministic block universe, a dynamic unfolding of quantum possibilities, or a simulation crafted by unknown forces, the search for meaning continues. As we navigate these ideas, we find ourselves at the intersection of science and philosophy, where the exploration of consciousness, reality, and existence beckons us to delve deeper. What if our entire reality is nothing more than an intricate simulation, crafted by creators who remain oblivious to our existence? This notion invites a cascade of questions. Are we merely an unintended consequence of a grand experiment? If our world is a synthetic creation, our designers surely dwell within a genuine reality, a tangible realm beyond our understanding. Yet, does this just shift the problem of existence to a higher level? Are we, in essence, trapped in a stack of realities, akin to the famous turtles all the way down adage? This perspective is often rooted in the assumption that a physical computer must be responsible for generating the calculations that underpin our universe. However, what if reality doesn't require a physical foundation? What if it exists solely through abstract calculations, divorced from any tangible structure? This intriguing hypothesis is championed by Max Tegmark, a Swedish-born physicist who posits a mathematical universe. Initially focused on cosmology, Tegmark turned his attention to existential queries about the very nature of reality. His vision parallels the simulation hypothesis, but it liberates itself from the constraints of a physical computational device. In Tegmark's framework, mathematics does not need a physical home, it simply exists in a realm of pure abstraction. This raises fundamental questions. Where, then, do these calculations occur, and what entity performs them? To Tegmark, the answer is profound yet elusive. Mathematics, in this context, exists as a fundamental reality, with no concrete origin or defined location. In his vision, our universe is not an isolated construct, but part of a vast multiverse teeming with every conceivable mathematical structure. Each universe within this multiverse is defined by its unique mathematical laws, allowing for an expansive library of possible realities, each as valid as our own. Imagine the possibilities. Within this boundless expanse, versions of ourselves exist in myriad forms, governed by varying fundamental forces, spatial dimensions, and mathematical rules. The library of potential mathematics is not merely vast, it may be infinite, encompassing not only the universes we can conceive but also those we cannot even fathom. The infinite sea of calculations could yield an endless variety of realities, from the fantastical to the utterly bizarre. One particularly unsettling prospect arises from this mathematical universe, the concept of consciousness emerging from random fluctuations within the infinite sea of calculations. At any moment, the right combination of mathematical structures might spontaneously coalesce to form a mind, a consciousness with memories and experiences strikingly similar to ours. In this scenario, you could find yourself contemplating the existence of an apple, reliving memories of your life, and believing fully in your reality. Yet this existence would be transient, a fleeting moment in the vast ocean of mathematical abstractions. Like a dream, it would manifest and vanish in the blink of an eye, leaving no trace. In the grand scheme of this mathematical universe, these transient minds would be dwarfed by the sheer volume of potential calculations. How can one be certain of their existence when they might simply be a temporary fluctuation? How do you know that your memories are authentic, that you weren't just conjured into being moments ago, or that you won't dissipate into nothingness before the day ends? Such thoughts may seem absurd, but they challenge our fundamental beliefs about reality. Even as these unsettling ideas unfold, the notion of a mathematical universe does not provide easy answers. There is an inherent discomfort in reconciling the idea of our cosmic existence with the notion of a future devoid of life. According to current cosmological theories, the universe is expected to endure for an infinite duration, eventually culminating in a cold, empty void after the last stars extinguish and black holes evaporate into nothingness. In this bleak future, the cosmos may seem devoid of activity, appearing lifeless and still. However, this vision of a desolate future may not capture the full picture of what lies ahead. To grasp the dynamics of this future, we must delve into one of the most misunderstood concepts in physics, entropy. Ludwig Boltzmann, a brilliant mind of the 19th century, made significant strides in our understanding of thermodynamics. He championed the atomic hypothesis, the idea that matter consists of indivisible atoms, during a time when this view faced significant skepticism. Boltzmann recast the laws governing energy flow in terms of atomic motion, fundamentally altering our grasp of thermodynamics. Before his passing in 1906, empirical evidence supporting the existence of atoms began to surface, validating his groundbreaking theories. As Boltzmann contemplated the behavior of atoms, he pondered their arrangements. Consider the air surrounding you, atoms of nitrogen, oxygen, and carbon colliding and interacting in countless ways. Every configuration of these atoms appears indistinguishable from one another. Yet, experience teaches us that atoms are unlikely to spontaneously cluster in a corner of a room. If we gathered all the air in one corner, it would rapidly disperse to fill the entire space. Boltzmann demonstrated that this phenomenon is merely statistical. Specific atomic arrangements evolve into more generalized configurations. This shift, from specific to general arrangements, marks the progression of entropy, a fundamental rule of the cosmos. The evolution from specific to general can also be viewed through the lens of energy. The total energy in any scenario remains constant, as dictated by the laws of thermodynamics. However, not all energy is equivalent, some is useful, while other forms are not. The growth of entropy signifies that useful energy degrades into a less organized, less functional state. Imagine a cylinder of compressed air, representing a highly specific state with a lot of useful energy. Initially, this scenario boasts low entropy. Now, as the compressed air escapes, its energy becomes less organized and more widely dispersed, leading to higher entropy. In a sense, the universe inherently favors disorder over order. This principle underlies the trajectory of our cosmic existence. To sum it all up, the exploration of existence, whether in the context of a mathematical universe or the reality of entropy, continually pushes us toward profound questions. Are we mere echoes of calculations within a vast multiverse? Will we eventually face a future where the universe fades into emptiness? Each inquiry leads us deeper into the labyrinth of understanding, where the boundaries of knowledge blur, and the nature of existence remains an enigma. As we reflect on these ideas, the interplay of consciousness, reality, and the very fabric of the universe presents us with a tapestry of uncertainties. Our understanding of existence, woven from the threads of mathematics and the laws of thermodynamics, invites exploration, speculation, and ultimately a deeper appreciation for the mysteries that surround us. Imagine a world where a simple twist of a valve unleashes the concentrated energy stored within a cylinder of compressed air. The rush of air that escapes can spin a wheel, generating electricity or powering a machine. Yet, this exhilarating burst of useful energy is fleeting. Eventually, as the pressures equalize, the airflow ceases, the wheel comes to a halt, and all the potential energy has dissipated. This pattern is not unique, it is a fundamental truth of every physical process. Energy constantly transitions from a useful state to a less useful, more dispersed form, an ongoing battle against the inevitable march of entropy. Entropy is the universal law that governs the degradation of energy. Think about it. Your body tirelessly works to maintain order and organization, fighting against the relentless increase of entropy. To sustain this struggle, you require a continuous supply of concentrated energy from the food you consume. However, in this process, you too contribute to the overall rise of entropy, excreting waste and emitting heat as byproducts. Since the universe began, entropy has been on the rise, and one of the persistent mysteries of cosmology is why it started with such low entropy. As time marches on, the available useful energy diminishes, ultimately leading to a cosmos filled with maximum entropy, a state in which no useful energy remains. The question then arises, what can occur in this maximally entropic universe, where energy is no longer capable of doing work? Enter the realm of statistical mechanics, where the rules of thermodynamics, articulated by figures like Ludwig Boltzmann, come into play. These rules are based on probabilities and statistical likelihoods, suggesting that even the most improbable events can eventually happen, given enough time. For instance, imagine the air in your room gathering itself into one corner, or billiard balls spontaneously arranging back into their original positions. While these occurrences are astronomically unlikely, Boltzmann argued that with sufficient time, they are bound to happen. The future universe will have one abundance, time. In this state of maximum disorder, order can occasionally emerge from chaos. Fluctuations will ripple through the fabric of the universe, creating temporary pockets of organization. Occasionally, these fluctuations can produce particles that briefly exist before fading back into the void. In extremely rare instances, these fluctuations may give rise to something more complex, a human mind, for instance. These fleeting consciousnesses are often referred to as Boltzmann brains. They are incredibly rare events, yet with an infinite timeline, they will occur repeatedly. What's more astonishing is the possibility that your consciousness, complete with memories and experiences, could materialize within this cold, desolate cosmos. The notion suggests that, if the universe were to exist for an infinite time, there would be countless instances where your exact mind comes into being over and over again. Given this perspective, it may well be more likely that you are a Boltzmann brain existing in a vast, empty universe than a physical being savoring a ripe, green apple. Each time you engage with this reality, you could just be a temporary fluctuation, one moment present, the next gone. As you ponder your existence, you might wonder if you've recently popped into being, poised to disappear just as swiftly. For a moment, reflect on the apple you're staring at. This seemingly ordinary object has ignited an extraordinary journey into the nature of reality. Your mind races through various philosophies, from Plato's ideal forms to the peculiarities of quantum mechanics and the complexities of holographic universes. However, as you ruminate on these abstract concepts, a primal sensation pulls you back: hunger. You focus on the apple once again, your stomach rumbling as you reach out to grasp it. You feel the smoothness of its skin beneath your fingers, the coolness that hints at the refreshment it promises. The simple act of picking up this fruit connects you to the physical world, an anchor in the midst of profound philosophical musings. You take a bite, the crispness of the apple awakening your senses, grounding you in the present moment. As the juice trickles down your chin, you realize that while the concept of being a Boltzmann brain in a universe devoid of energy may be intellectually stimulating, it also brings forth a fundamental truth: you are here now, experiencing reality in a tangible way. Yes, the implications of statistical mechanics may suggest that your existence is a mere fluctuation, but you also embody consciousness and awareness. This moment, with the apple in your hand and the bite lingering on your lips, reminds you of the richness of existence. Even in a universe trending toward maximum entropy, the capacity for experience, whether fleeting or lasting, brings color to the otherwise gray tapestry of the cosmos. Reality, in all its complexities, feels vibrant and immediate. In this sense, your journey through the philosophical and scientific realms has brought you full circle. The apple, a simple piece of fruit, becomes a symbol of the interplay between existence and non-existence, between consciousness and entropy. As you savor each bite, you affirm your reality, holding on to the preciousness of the moment, even as the universe continues its inexorable drift toward disorder. Copyright 2024 by AudioBooksTube. Thank you for listening. Please consider to subscribe, like, and share to help the channel growth. New videos on a daily basis.